by Matheus. Um, we and him were unlucky about the COVID, but we are very happy that he's recovering well, so he has enough power to deliver the talks. Matheus, today is like, it's all on you now, like the whole day. This lecture, next lecture, I hope you people had the opportunity to look at his exercises that are posted on the webpage. So we also have the practical activities and the questions. So we kind of squeeze Matheus. If you are tired, let us know, please. But anyway, we are lucky enough that he can deliver this, all these activities remotely. And so let's start with the second lecture. Thank you.
All right, thank you. And first of all, sorry I can't be there. It was actually very fun after my first lecture to talk to all of you. So I'm very sad we can't interact in person, but such is life. Do you say I have power to deliver all of this? We'll see. Hopefully we get to the end and you're not too bored by me. So, okay. The plan for today in the two lectures that we have is for the first one, talk about neutrino masses and some of the phenomenological consequences of it. So review a little bit of the material we covered in the first lecture. I'm going to create a little diagram to tell us exactly what the situation is in terms of neutrino masses and what they mean for new physics. And then we'll explore the phenomenology of each case. So the first thing I'm going to do is this diagram. So if you look at the standard model and you try to extend it, oh, and I should say, if you have any questions, please do interrupt me. I'll ask, I don't know, Martin, if you have a microphone or something. If someone raises their hand, just let me know and I'll stop until you have a chance to give them the mic. Okay, so first thing I want to do is try to understand the consequences for new physics. So everything in green will be new physics related.
I'll be watching here if there are questions.
Okay, thank you. And the first kind of choice that you have when extending the standard model to account for neutrino masses is whether or not you have a right-handed neutrino. So we kind of create two paths here. So in one case, there is no right-handed neutrino. In the other case, there is one. If there is a right-handed neutrino, then you're always allowed to write down a Dirac mass term. But remember, this doesn't mean that neutrinos are Dirac. All it means is that you're allowed to write down something that looks like nu C, okay, through the Higgs. So this term exists. It doesn't mean that neutrinos are Dirac. We'll have to see whether the right-handed neutrino nu C, in this case, is the left-handed antineutrino, just remembering that. If that particle carries a Majorana mass, then everything becomes Majorana in some sense. We'll see a little exception to that in a second. So in this case, if there is such a Dirac mass in this new particle, then it's clear. There's just some new particle. So that's the kind of new physics in that scenario. Now you have to ask yourself, on top of that Dirac mass, what else is happening? Suppose in one case that the mu term, maybe let's write it over here, that the mu term is exactly 0, where mu, so this I'm going to define as MD, and mu was defined as the Majorana mass of the left-handed antineutrino or right-handed neutrino. In that case, if mu is exactly 0, then neutrinos are Dirac. Exactly. And in that scenario, the type of new physics that you've discovered is that there is a new symmetry law. I'm going to put here law. In that case, that would be lepton number. L is conserved. The other option is mu exists, but it is actually very, very small. Okay, so the right-handed neutrino or left-handed antineutrino actually does have a Majorana mass, but it's a very small number. In that case, neutrinos are what we call quasi-Dirac. I'm going to put here quasi. And what that means is just that neutrinos are almost Dirac particles, except there's this tiny Majorana mass. We'll explore exactly what happens in terms of phenomenology there. And there, what you've discovered in terms of new physics is actually something quite interesting, which is there's a new hierarchy, a new hierarchy of scales. So mu is much, much smaller than MD, which is much, much smaller. Well, in this case, we could even put mu as much, much smaller than the VEV of the Higgs. Remember, this was 246 GeV. As far as the standard model goes,
Matheus, sorry,
this scale is the only.
Yeah, we have a question.
Hi, Matheus. Why are you saying that it would be a new symmetry? Because despite L is like an accidental symmetry is there, right? So why would this be like a new symmetry if neutrinos are Dirac?
So this is why I said it's a symmetry law. In a sense, it's my own interpretation of it. And remember, we were saying that everything that is not forbidden is mandatory. The standard model without neutrino masses, lepton number was just accidentally conserved. So you have that symmetry just kind of as an accidental consequence of the particle content and the forces that you have. In this case, you have this term which is perfectly allowed in the theory, but for some reason, and in this case, you interpret it as the consequence of a new symmetry, that term is exactly zero. It doesn't have to be that the only thing that you're enforcing to make mu equal zero is lepton number being conserved. So you could have lepton number violation elsewhere in the theory. Let's say there are more particles, but this is kind of the most minimal thing that you would do. It could be that right-handed neutrinos have another quantum number that is separate from everything else that the standard model carries, that is also conserved in such a way to forbid such Majorana mass terms. But the most minimal scenario is this one, where if neutrinos are Dirac, you can conclude that there is a new symmetry, in this case, lepton number. And then notice that I said it's a symmetry law. It's just not an accident anymore. It's something you have to impose.
Oh, I understand that. Thank you.
Thanks.
Okay. So those are two possibilities, which are basically Dirac neutrinos. And here, obviously, there is another way I can phrase the new physics in this quasi-Dirac scenario is there is a new scale, right? New scale. Obviously, this will happen in the next situation, which I didn't give myself a lot of space here. Maybe let's put it over here. And the next scenario is where mu is much, much larger than the Dirac mass. And in that case, neutrinos are Majorana particles. And again, not only have you, in that case, discovered a new particle, but there is also, again, a new scale, right? And now, depending on what the value of this Dirac mass is and what the value of mu is, it's possible that there is another kind of hierarchy that you've discovered, and that could be that mu is much, much larger than the vacuum exploitation value of the Higgs, which is interesting. Okay, so you see these three cases where after introducing a new particle, you actually have this ambiguity of where to go afterwards. Each one of them implies something new about the standard model, so it's a step beyond what we know in the standard model. And they have consequences either for fundamental symmetries or for just hierarchy of, in addition to consequences for hierarchy of scales. So that's our diagram so far. So if there is a right-handed neutrino, you have all of these ambiguities. Of course, there are more arrows. There's a lot of models out there that will have many different branchings of these different possibilities. Some of them can exist at the same time. You could have some right-handed neutrinos that have no Majorana mass with other right-handed neutrinos that do carry a Majorana mass and things like that. But this is kind of the minimal picture. And I want to make this kind of as clear and minimal as possible so we understand qualitatively what it means to go through each one of these paths. So the other option is there is no right-handed neutrino. And in that case, the most minimal thing that you can do to give Majorana masses, to give neutrino masses, is to actually give them a Majorana mass. Okay, so neutrinos in this case are Majorana. By definition, because you cannot write down a Dirac mass term without your partner of the neutrino, nu-c, that term doesn't exist. So this is kind of interesting because if neutrinos are Majorana, then consequently you've discovered that lepton number is violated. And that's also consequential. It means this accidental symmetry we had in the standard model, not only was it an accident, but actually it turned out not to be true at all because of neutrino masses. Now, this Majorana mass may come from something completely new, some kind of exotic physics, but the simplest thing that you can do in this new bifurcation here, so there are no exotics. I can talk a little bit about what that might look like. So in that case, if there's no other exotic particles in your theory, then the only thing you can do was write down the Weinberg operator. And remember, the dimension of that operator was 5. But in reality, you could imagine similar operators at higher dimension. So I will put here, instead of equals to 5, you could imagine Weinberg operators, quote unquote, that are either dimension 5, or you can dress them in particular ways to get higher dimensional things that look like the Weinberg operator and give the same type of phenomenology and consequence that at low energies, all you really have in terms of the physics described by these things are Majorana neutrino masses. And here, even though we cannot say what's behind this operator in principle, what you've discovered in this case is there's the existence of a new scale, which in this case we're calling lambda UV. Remember, the Weinberg operator looked something like this. We squared that thing, so this was dimension 3/2 plus 1. And we were basically squaring the whole thing. So this is dimension 5. And our Lagrangian had to be dimension 4. So we divided this by some new physics scale, lambda UV. I'm calling it lambda UV because this new scale has to be associated with high energies, so the ultraviolet part of the theory. It doesn't have to be, like, for example, Planck scale, but It will be something that you expect to be much larger than the scale of light neutrino masses. Whether that's 10 times larger or 10 to the 10 times larger, we still don't know. But in that case, if there's no exotic particles, then all you have is the Weinberg operator, and you have this conclusion, and there's a new scale lambda. And then obviously you could imagine that theorists are very creative, so you could imagine some other exotic things. And in that case, even though the right-handed neutrino may not exist, you could imagine other scenarios where, for example, there are many things you could conclude, but for example, you could imagine some ultralight background field, let's say some ultralight scalar, that due to its abundance in the universe, in the region of space-time, as we create, they interact with this scalar in such a way as to look like they have masses. So there are other possibilities here. This is just one of them. But in this case, obviously, the existence of new particles or physics, right, in general. So obviously, this possibility of exotics can also happen in the case of the Dirac mass. So maybe I should also do an arrow from this to that. But it's less interesting in the sense that you can make everything work with the existence of new C as far as neutrino masses go, while in the case where there is no new C, the exotics are really like the ingredients that's necessary for neutrinos to get mass. So this is the diagram that I wanted to show. If you don't take anything else away from today or from the previous lecture, this has to be it. I think this was my attempt to make basically the argument as to why neutrinos are beyond the standard model effects and interesting beyond the standard model effects. I think all minimal possibilities of how to add neutrino masses to the standard model lead to some kind of new physics, whether it be consequences for fundamental symmetries or for new particles. So I'll stop here and ask if there are any questions about this diagram.
Yes, there is one question.
Could you explain a bit more why you mentioned the ultralight scalar? Is it like, are you referring to what might be behind the Weinberg term, or what is it about?
No, so I didn't want to get into the details of this, but you could imagine some particle that couples to neutrinos in some specific way. Well, actually, I cannot really write this down in a way that. Let me think about this. So, because, yes, I made my life kind of difficult here. But you could imagine, for example, I cannot imagine, actually. So this was perhaps a bad example, but I'll try to illustrate it with the new C field. One way in which fermions can get a mass from a background field. So let's say I have this new C field. Obviously, I cannot do that in this region of the diagram because there is no right-handed neutrino, but let me just kind of tell you how one might get a mass out of an ultralight field. You could imagine some term like this in your Lagrangian that basically couples this light scalar to two fermions. This looks a lot like the Majorana mass term, but it's just the scalar. But if this scalar has some finite density in the background, you could imagine that basically the finite density of the scalar basically behaves like the VEV of the Higgs. And in the end, you would get something that looks like exactly the Majorana mass, where this mu parameter is proportional to the density of the scalar rho, the density in the background. So this is kind of a more exotic type of physics. I kind of made my life difficult because I'm talking no right-handed neutrinos in this case. Obviously, in this arrow here, such terms could exist. But for the no right-handed neutrino case, maybe that's a little bit harder. You have to work harder on the model building side. But that's the general idea. You could imagine some exotic effect where, in this case, a finite density background field generates neutrino masses in this way.
Okay. Would it just like quick comment? Would it be like analogous to the Higgs mechanism, or like because it's a scalar, but
it's similar. It's similar in a sense, but so for the Higgs, when we wrote, so for example, let me write another term here. Let's call this phi prime nu c. Okay, if phi prime also develops a vacuum expectation value like the Higgs does, okay, then you would write this term like something like this. And this component, which is this constant associated with the symmetry breaking scale of this new scalar phi, it should be phi prime. This term is exactly the analogous term for the Higgs mechanism mass. So that would just give your new C on the mass term symmetry breaking in a very similar way to what the Higgs mechanism does for standard model particles. But in the case of a finite density background field, this is not exactly what's going on, because you actually have a finite amount of occupation number of this scalar particle in the background. And if it's an ultralight thing, one way to think about it is we have a field kind of similar to like an electric field or so, where as neutrinos propagate through this field, they look like they have a mass, but it's not a mass in the usual sense of the word, if that makes sense.
Yeah, it's an exotic way to another exotic way to produce their mass. It's a lot clearer now. Thank you.
Yeah. So the Higgs, when it gives masses, you don't need to have like a number of Higgs particles in the background for that to work. In this case, you do need it. So this particle has to be produced in the early universe and has to be around today for this to work. Okay, so with that, this is kind of the diagram that I wanted to show. I also wanted to clarify a few things from the first lecture. Many of you were confused with my notation, and this is 100% my fault. So let me just clarify the math notation a little bit. Okay, so clarifications. The first thing is when I talked about Majorana masses, I drew this kind of diagram. And there's some mu here, for example. And I was talking about chi. And in the Lagrangian, we had something that looked like mu chi. And for those that are a little bit more in the know here, this is a two-component spinner. So it's actually a little vector. And what I really mean by this term is chi transpose epsilon chi. So that's the kind of dot product that I'm doing in this case. The other thing was diagrammatically, it looked like I had these two arrows flashing, and in fact there are two ways to draw this type of diagram and two conventions for arrows. And it turns out in the case of Majorana fermions, the two kind of look the same. And what I really should have written in these diagrams was actually chi bar, and in the same thing here, chi bar. And the second type of arrow is basically particle number. So if this was, a lepton, once I insert this mass term, this actually becomes an anti-lepton, hence why the arrows are clashing. In the case of the first arrow, what they really mean is like the type of fermion as far as the chirality goes. So these are chiral arrows, if you want. So what it really means is that on this side, you have something that looks like overall a left-handed thing. And then the other side, you could imagine this looking like a right-handed thing. So the mass flips the two types of chirality, hence why the arrows are always clashing. When it comes to chiral arrows, for the mass term, they're always clashing, but they are only clashing in the case of Majorana masses. So if I were to do the same for the Dirac masses, the first type kind of term looks exactly the same. Except now I have a different type of fermion. And the second type of arrow actually looks the opposite, where the particle number, in a sense, the particle number is the same. So here's the Dirac mass. And remember, we were kind of hoping that the quantum numbers of chi are basically opposite of the quantum numbers of eta. And in the end, what's happening is this is the fermion, or if you want, if it's a lepton, it would be a lepton. And when I bar the particle that has minus the quantum numbers of the first one, what I'm getting is also a lepton or also a fermion. So a Dirac mass basically keeps the particle number the same. So it doesn't, this is also a way to think about this term violating all quantum numbers by 2 units. And this one, potentially, if this is true, keeping the quantum numbers the same. Okay, so that's just a little clarification. And again, in the Lagrangian, we had something that looked like MV chi eta. And again, what I really mean by this is the transpose epsilon eta. Okay, where these are two separate two-component spinors. All right, any questions about this? If not, let me move on to kind of new content here, and it's still more or less old stuff. But let me look at a Dirac mass for an electron, for instance. I'm gonna kind of forget a little bit the Higgs in this story. So these are Dirac mass, E and EC. And to clarify, again, E is a left-handed electron. EC is a left-handed positron. And when I draw E bar, I flip the chirality of this particle and also its number. So E bar becomes a right-handed positron, which is not the same thing as the left-handed positron. It's a different field associated with the first one here. And EC bar then becomes the right-handed electron. Okay, so this is the notation. And what I wanted to do is go back to the Lagrangian, which looks like EGC. There's a Hermitian conjugate term, and I want to collect this into a matrix form. And the way to do this is to just, you can show that you can just collect everything in these little vectors. And you have a matrix sandwiched between a transpose vector and a column vector. And at the end of the day, this whole thing, after multiplying the matrix out by these two vectors, you will get just a series of numbers that will make up your Lagrangian. The first term here is the thing that is going to connect E with E, which remember is like the same fermion coupling to each other. So that's how my random mass term. For the electron, that's forbidden. For the also EC, that's also forbidden, but the term that connects the two is allowed. So this matrix is actually symmetric, and you get this factor of a half in the beginning because I basically have these two off-diagonal components. Once I multiply this out, you get those two mass terms, and they combine to give you this first thing. Okay, this is what the mass matrix looks like. Now, a few things that are very useful in terms of this, let me also call this M, capital M. A few things that are very useful is to remember some linear algebra relations. The first one is that the trace, I should say, what we really want to do here is diagonalize this mass matrix in order to get the masses of the actual propagating degrees of freedom, the ones that have a well-defined mass. Remember that E and EC are connected to each other, but they're not actually, there's two independent fermions that couple to each other. But what you want to have is a single fermion that has a well-defined mass propagating. That makes our life easier. And some relations that are useful is that the eigenvalues of this thing, of this matrix, are actually equal to the trace, and the determinant of this matrix is the product of the eigenvalues. Okay, so obviously for this particular matrix, so for M, this is 0, so that's interesting. But the product of eigenvalues is actually minus MD squared, and from these two things, you can deduce that one of the eigenvalues is MD, and the other one is minus MD. This looks kind of problematic because there's a minus sign there. It turns out this minus sign is kind of harmless. These fields, they're defined often up to a full complex phase rotation. So you can always rotate these fields in such a way that you get rid of these minus signs. But it's also perfectly okay to work with a theory carrying out these minus signs everywhere. But at the end of the day, never in a physical observable that depends on the math, you're going to have something that looks like a negative math is, like something that couples to gravity in a weird way. This minus sign mostly has to do with the CP properties of the field, and you can always rotate it away. So the minus sign is harmless, and it's there. And it's kind of interesting because what you're seeing here is after diagonalizing this matrix, you have, in all generality, let me write this down. So there's a cosine theta of E minus a sine theta of EC. And there is a E minus, which is sine theta E plus cosine theta EC. Okay, for our specific case, what is the rotation that we needed? Because in order to diagonalize this matrix, we had to rotate things. And another very useful formula that you're going to need also for the exercises will be useful there is that for a symmetric matrix, when you diagonalize it, the rotation angle to diagonalize that matrix is given by, let's say I have in this case 2C or B minus A, where the matrix that I'm thinking of looks like A, B, C, C. So that's the mixing angle. And for our specific case, tan to theta looks like twice the Dirac mass over 0, which obviously goes to infinity, and that's okay because this tangent is just the tangent of 90 degrees. And therefore, the angle theta, because this 2 times theta, is 45 degrees, or pi over 4. This situation is what's called maximal mixing. And it's the case where you basically rotated the system in such a way that the two physical particles become maximally mixed. So none of the mixing angles are small, basically. That's what it means. They're maximal. So now oops, I did this the other way around. This should be minus, and this should be. So what you see here is that the notation now becomes very evident. So E minus, the physical degree of freedom, E minus, is just the difference of the flavors of these two fields that are coupled to each other, and E plus is the sum. So if you were to write down the mass matrix in terms of those fields, obviously, since we diagonalize, what it means is that in one case, I have a positive mass, in the other case, I have a negative mass. Okay, so that's your 2 degrees of freedom. Those are the actual particles that are produced in the experiment. And often, very similarly to what Pedro has taught us about neutrino oscillations, what is really happening here is you're producing superpositions of E plus and E minus in whenever you produce electrons. But you never see oscillations between the left-handed electron and left-handed positron, mostly because, first of all, charge is conserved, so we have to put the bars in the right places, which I haven't been very careful with. But also, regardless of that, the two particles have exactly the same mass. So what that means is any phase difference between the particles never really appears because the time evolution of the two states is identical because they have the same mass and in a sense the same energy, always the same energy because they're produced in the same way. So this is the story for an electron, and that will make our lives kind of easier when talking about neutrinos. So let me go back to neutrinos and explore the scenario that I was calling quasi-Dirac. So now I want to make mu much smaller than md. If we collected our mass terms into the matrix with the right-handed neutrino, we have 0 in the upper left because there were no new terms at the dimension 4 or smaller. You have your Dirac mass, and you have the mu term. Okay, I highly encourage you also before the exercises, maybe I should put it there, just diagonalize this matrix by yourself fully. It's not that difficult, just to see what you get. But in the end, under the assumption of mu much smaller than md, again, the mixing angle, theta tan to theta, is twice md over mu. And this is much larger than 1. So I can approximately take theta again to be pi over 4. If mu is exactly 0, we recover the case of the electron. If mu is not zero, but it's very, very small, then you're just a perturbation away from this electron case. So the physical degrees of freedom, the ones that propagate with the definite masses, look like this. Square root of 2. And you see here, I should put a tilde, because theta is not quite pi over 4, because this is not quite infinity, but it's pretty close. But the masses are slightly different. And I can write down the masses as m plus minus md plus or minus mu over 2. So in terms of a spectrum, what you have is, if you don't look too closely, you have nu plus and nu minus on top of each other. But if you look closer, there is a kind of a hyperfine splitting situation going on, where the middle here is given by the value md, and the separation between these two things is given by mu. Okay, and this kind of setup where you have a Dirac fermion that has been split a little bit by a Majorana mass is called a quasi-Dirac fermion. Again, these are two separate fermions, nu plus and nu minus. When they're degenerate in mass, usually we go back to just calling them a single fermion, which is a Dirac particle, but it actually has all these 2 degrees of freedom inside of it. When you split them, you still kind of basically call it a single particle, but it's a quasi-Dirac particle. But the real physical thing, the correct thing, is that there's actually 2 separate fermions in there. Any questions here? Okay, then let me move on to understanding what this means for the phenomenology. And the first thing to note is that nu was something that interacted with the standard model. It was inside of that lepton doublet, and this thing had weak interactions, right? So this talked to the W boson, the Z boson, and so on and so forth. But nu C was actually fully sterile. The kind of minimal option for introducing nu C is for it to have absolutely no interactions whatsoever. It doesn't have any color, it doesn't have any weak isospin, and it doesn't have any hypercharge, and also no electric charge as a consequence. So in the experiment, when you produce neutrinos, you produce them through the weak interaction. So the real fermion that you're actually producing is nu, the state nu, which is a superposition of these 2 physical basis fermions, right? So nu plus nu minus. And these are propagating. And this is the interaction state. Notice the similarity with what you're seeing with Pedro. There you had mixing angles. It was a 3 neutrino paradigm. But right here, I'm not talking about flavors. I'm assuming a two fermion nu and nu C, but they are actually just a single family of the standard model. I could have called these nu E's, for example, just to be a little bit more precise. The index E on the nu C fermion is a little bit more ambiguous because it doesn't really interact with the electrons. So just kind of more arbitrary, but you could have chosen to call it that, right? Since it couples to nu E through this mass term. So that's the interaction term, and this is the 2 propagating degrees of freedom. when you evolve this particle, so this at a time t, in something that you already know how to do from previous lectures, you have something that looks like E plus T, nu plus, and then I, E minus, T, nu minus. Again, remembering that neutrinos are always ultra-relativistic, what you have is this thing looks like the momentum of the neutrino, which I'm assuming to be the same for all particles being produced, plus a term that is the mass squared over 2p, and the same thing for the minus. And at the end of the day, if I were to compute what is the probability that a neutrino is produced, and then I still detect it as a neutrino, you would find that this is basically this expectation value squared for the probability. And at the end of the day, what this depends on is actually the difference between the phase evolution of these two states. And you can show that this difference, okay, is what I'm going to call delta m squared over 2p times, oh, I haven't put the time yet. Delta m squared over 2p, which is m plus squared minus m minus squared 2p. In terms of the small parameters, this, let me zoom in here. This delta m squared, you can rewrite it as twice mu mv. You can just show that. So the mass splitting between these two states is proportional to this very small number mu, which is splitting this Dirac fermion into two things. And at the end of the day, what you have is something that looks a lot like the oscillation terms that you derived with Pedro, L over 4e, with one exception. You see that there is no mixing angle factor in the beginning here as a prefactor. And what this means is because the mixing angle is maximal between the two states, the oscillation is also maximum. If you were to plot this oscillation probability, I'm going to make this very large, as a function of L for fixed E, for instance, or I could have chosen to do L over E, whatever. So P for a neutrino to stay a neutrino, and what that really means is for an interacting neutrino to stay as an interacting neutrino, which is the one that sees the interactions, the weak ones. This probability is 1, right? You see for L equals 0, that's just 1. Oh, bad. What I meant is 1 minus sine squared delta square L over E. And that would be just 1 because this sign goes to 0 at L equals 0. And it stays like that until you start getting close to the oscillation frequency. And eventually you average out this being a half and this being exactly 1 and this being exactly 0. So this oscillation from this quasi-Dirac splitting actually goes from what you call a survival probability of nu to nu of 1, where there's no effect, to 0, where the effect is maximal. So if you know how to find the oscillation frequency of this system, it will be really hard to miss the fact that neutrinos are actually not going into like becoming interacting. They're actually, in this case, all of the neutrinos look more like the sterile component than they do as the interacting component. So this is the quasi-Dirac picture. It is very interesting because you have this very kind of smoking gun signature, basically a maximal disappearance of neutrinos. But it's also very challenging to test. First of all, because if you're not at the oscillation frequency, there's basically nothing you can see. But if you're past the oscillation frequency and you averaged out the oscillations, it's just the energy independent factor of half of your neutrinos disappear. So here you have basically half of your neutrinos look like the interactive state, and the other half look like the sterile state. One great way to constrain this is using solar neutrinos. Solar neutrinos is actually quite well understood, at least better understood than the factor of a half, right? So if half of the solar neutrinos were to disappear on top of the normal oscillations that we know of, you would definitely know. So if you're in this situation for solar neutrinos, you would definitely be able to constrain it. If you're in this situation for solar neutrinos, you absolutely will be able to constrain it. But if you're here, then not so much. So what you need is, let's say your delta m squared is such that you get a mu of 10 to the minus 10 electron volts and MD of 0.05 EV. So MD is just, it has to basically match the overall scale of neutrino masses, right? So it has to be that. And mu is this very small Miranda mass, which gives you this tiny splitting. If that's the case, then your oscillation frequency, like in this case, where you get the maximum effect, will be, you can calculate 10 to the 11 meters, which is 1 astronomical unit. Okay, so what that means is, here's the sun. As neutrinos propagate to the Earth, if mu is smaller than 10 to the minus 10 EV, then you're somewhere in this range. Okay, where oscillations can happen either maximally or in the averaged out regime. And that means you can exclude, so solar neutrinos basically require, the limit here is that mu be larger than 10 to the minus 10 EV. If you were to draw like a line of mu where mu is getting smaller on the right, I'm gonna kind of play a trick on you here, where this is 10 to the minus 25, let's say, electron volts, and this is 10 to the minus 5 electron volts. If it's larger than 10 to the minus 5, we recover that limit that I think someone asked me in the first lecture, where mu is similar to MD. And in that case, you basically start getting more oscillation frequencies in the normal oscillations than you would expect. So solar neutrinos basically exclude everything below 10 to the minus 10, above 10 to the minus 10 EV. After that, it becomes a lot more challenging because the oscillations happen at much larger distances. So you need to go to kind of other astrophysical scenarios. You certainly cannot do this at Earth. And another good example of that is, as Pedro told you yesterday, IceCube can see individual neutrino sources. And for each of the sources in IceCube, we can ask the question, am I seeing an oscillation that is consistent with this kind of full disappearance of neutrinos? So for each source, you can try to constrain a region of this parameter space. If you live up here, it's actually very difficult because you don't know the flux of your source. So even if half of your neutrinos were to disappear, you just wouldn't be able to tell. There's no energy dependence there. But if you are exactly here, then you're in luck. So these things you can do with neutrino telescopes like IceCube, KM3net. And I'm not sure if Pedro mentioned, but I'm also just going to add future projects. If you're kind of curious about what they might look like, let me know. But you have other neutrino telescopes like P1, which is a project off the coast of Canada, and Trident, which is a project for the South China Sea. And all of these things, if you couldn't gather enough data about sources, you can start constraining this parameter space. And then at the lowest and lowest values of mu, you can constrain them using supernova neutrinos. So for example, supernova 1987A, it's very far away, like 50 kiloparsecs, and it's very low energy. So your L over E is very large, which means to get an order one, what you really need here is delta m squared L over E to be order one in order to be in this region. So if L over E is very large, delta m squared can be very small for you to see the effect. And then even lower than that, you could imagine constraining this using the diffuse supernova neutrino background. I don't know if you saw that in Pedro's lectures, but all this really is just a collection of all supernovae in the universe and the neutrino flux associated with that. So that's the story for positive Dirac neutrinos. I think one of the more interesting consequences of this is exactly why is mu so small, right? Much smaller than the electroweak scale. And this is, in a sense, kind of a different hierarchy problem. And this could be a very kind of interesting scenario if you were to discover such such dips in the neutrino propagation. It would be a smoking gun signature that neutrinos are Dirac-like, and you call them quasi-Dirac. And two things, there will be lepton number violation in nature that is very, very small, when neutrinos will be basically Dirac particles. That's the story. Any questions on the quasi-Dirac story? I think I don't have much time left, right?
Questions? I will go for one, okay?
Okay.
Hi, Matheus. For the astrophysical sources we know so far, the L over E is more likely to sit in the region where we have half, or can we be close to the oscillation dip?
It depends. So I think the better way to phrase it is, given a source, you have an L and you have a spectrum, hopefully. I think so far the sources are more like you have a source with a few events, right? So that's kind of the challenge, is you don't have a spectrum. But let's say you have a source and you know the distance to that source. And what you do at the end of the day is, like, there's some events, let's say, you know, IceCube has some events there as a function of energy. A number of events. What you do is you look at this spectrum and say, for the neutrino energies that I have available to me, do I see something consistent with the disappearance of neutrinos? If not, then given that L over E, you go in this region and let's say it corresponds to a delta m squared of that value, and you can constrain it. Just to give you an idea, for the current sources, the typical delta m squares that you're looking at is around 10 to the minus 13 EV. Sorry, the typical mu values, 10 to the minus 13 EV, all the way down to 10 to the minus 17 EV. It's still very early days, so this is kind of it's something that has been known for a very long time, but only now that we're starting to gather more data from neutrino sources, you can start actually constraining this. So the answer to your question is, there is a lot of open parameter space in this kind of line where, you know, for a lot of the sources that IceCube or these other neutrino telescopes could see, you can make a statement.
Okay, one more.
Thank you. Hi. It is not quite clear to me when you do the graph of the probability. Can you go to the previous slide where the formula is, the sine square? The E is the difference of the energies of the neutrino plus and neutrino minus.
Right. Maybe the better way to do this is to call this, is to call this P. Because, and this is kind of subtle. I think Pedro mentioned this a little bit. What you're assuming in this system is that the two neutrinos that are produced, nu plus and nu minus, they're produced with exactly the same momentum. That's the assumption under this derivation of the oscillation probability. But after everything goes through, it's perfectly okay to replace the momentum by the energy, because the mass correction to the momentum, to the energy is very small. So this is either P or E. Numerically, it makes very little difference. It's only on the difference of the phase evolution that the mass matters. Precisely this formula here.
Okay. And for the difference of the masses, you compute several values and...
Yeah, so actually I should have said in this plot, so you could have done this plot like this, fixed delta m squared. And then this oscillation frequency basically looks like, let me see if I'll get this right, E over delta m squared. There are other numerical factors here, but basically means that I can define this quantity L oscillation, looks like E over delta m squared. And if you do that, actually your oscillation probability looks like 1 minus sine squared of L over L oscillation, and up to numerical factors of order 1. And when L over L oscillation is 1, that's when you hit this dip, this dip here.
Okay, thank you.
Another question.
Hi, Matheus. Can you go to the previous slide? Why did you say that in the definition of nu plus and nu minus that there is not an exactly equality?
Oh, because of this, basically. So in the case of the electron, when we did this diagonalization, theta was exactly pi over 4, because the tangent to theta was exactly infinity, if you want. So there was a 0 in the denominator here. In this case, this is not 0, so this is much larger than 1, but it's not quite infinity, if you want. So if you want, theta is pi over 4 minus a little epsilon, okay, which is like going to depend on mu over md, which is a very, very small number. And what that means is when I write down, this combination of what the mass basis looks like in terms of the interaction basis, these cosine theta and sine theta, they're not quite 1 over square root of 2. They're like 1 over square root of 2 plus or minus a little epsilon. But that little epsilon basically doesn't matter as far as the mixing is concerned. Does that make sense?
Yeah. Okay, I got it. Thank you.
Okay, we have 2 more questions. So I will go to these 2 and then we stop and we have another lecture at the afternoon and then also we have a question section. So I will take 2 more, okay?
Okay.
Hi, Matheus. I think I just got confused with the flavors. So we would need to have one sterile neutrino for each flavor, or it would be the same when we are doing this computation for each flavor. We call the same sterile neutrino. These change things or not?
Right. So, this is a major simplification of the picture. So I'm just assuming one family, which this would be new E, new mu, or new tau. And then I'm attaching a new sterile neutrino with that neutrino. So there's new E and new EC, right? That's the sterile fermion. In the full picture, you have a choice also. You have new E, new mu, new tau, and then you could have, let's call them new EC, new mu C, and maybe new tau C. It's a choice. I mean, if neutrinos are quasi-Dirac, then you need all three, because for every neutrino you need a mass, and if all three neutrinos are massive, you need all three. If only two neutrinos are massive, which is still perfectly allowed by data, we only know two mass splittings, and we don't know the absolute scale well enough, then you only need two sterile fermions. Only two neutrinos are positive Dirac fermions, and that's the end of the story. You have one light neutrino, which is this kind of exotic massless fermion. And that's okay, perfectly allowed. In the full picture, let's say you were to have three sterile neutrinos, then this calculation that I just did becomes a lot more complicated, because this matrix, the mass matrix M, is actually something that looks like a zero matrix that is 3 by 3. Let me specify the basis also. This is nu E, nu mu, nu tau. And then in all generality, okay, you could have, let me label them by numbers now. Nu N C. So there's N sterile neutrinos. This is always 0 on the top left-hand corner. And then you have a Dirac mass matrix. And this is a N by 3, if I got my dimensions correctly. No, excuse me. This is a 3 by N. 3 by 3 plus N, I should say, actually. And then there's MD transpose. And then here, let me call this M, and that's an N by N mixing matrix. No, this is N, right? Sorry, my brain is barely functioning. Let's see. MD is a mass matrix that connects the active neutrinos to these sterile neutrinos. So it has this kind of at least 3 in one dimension, but N in the other. And then you have this M, capital M matrix. Maybe I should have called this something else, but this capital M is N by N, meaning you have all of the Majorana mass terms of all of the sterile neutrinos. And there could be a huge number of parameters inside of this matrix. But at the end of the day, the kind of structure that you would have is always that these parameters are small and these are of the scale of neutrino masses, if that makes sense. So the full picture is actually a lot more complicated. What I'm doing here is just active sterile, but in general, you have nu E, nu mu, nu tau active, and then however many arbitrary sterile fermions you have.
Okay, thanks. So the last question we will leave to the afternoon because it's taking longer and we need to move to the next part. So see you in the afternoon, Matheus, and thanks.
Okay, thank you.